So today we are going to begin talking about thermal actuation. And for the most part, we are simply going to review. You guys can't see anything, son of a. Give me another minute to turn on the projector. I'm losing my mind today. All right, let's try this again. We are going to be talking about thermal actuation today. Specifically for today's class, we are going to review some simplistic heat transfer fundamentals. So there are four possible mechanisms for heat transfer to occur. So the movement of heat from one point to another. The first is thermal conduction. So thermal conduction describes heat transfer through a solid medium from one point to another. Mathematically, thermal conduction is described by the following equation. So we're going to have Q double prime subscript COND. So this term here represents the conduction heat flux measured in watts per meter squared. And this quantity will be equal to negative capital K. Really, there should be a Greek letter kappa, but I can't make it look any different. So I'm just going to use capital K. This is the thermal conductivity measured in watts per meter Kelvin times the derivative in temperature with respect to X. So this gives us conduction along a specific axis. Okay. Our second mode of heat transfer is going to be natural thermal convection. So in natural thermal convection, heat transfer occurs from a surface into a stationary body of fluid. So a temperature gradient in a fluid induces local flow movement, local flow movement, so a temperature gradient in a fluid local flow movement through buoyancy. The fluid movement is what facilitates the heat transfer. There is a mathematical equation that governs this, but it's the same mathematical equation that governs forced thermal convection, which we're going to talk about next. So I'll introduce the equation once we talk about what that is. So forced thermal convection is heat transfer to a body of moving fluid. The bulk movement of the fluid provides enhanced heat transfer as compared to natural thermal convection. So mathematically, this is described as Q double prime convection, where this is our convection heat flux, also measured in watts per meter squared, will be equal to H. So this is our convective heat transfer coefficient. Measured in watts per meter squared Kelvin. And this convective heat transfer coefficient is effectively multiplied by the temperature at the endpoints of the system. So this TS is going to be a surface temperature measured in Kelvin, and this T infinity is a fluid temperature measured in Kelvin. So the value of H depends on a number of things, okay? H depends on surface geometry, fluid velocity, viscosity, and thermal diffusivity. In general, we can give you ranges of appropriate values of H for different conditions. Okay. So I'm making a simple table here. So let's talk natural convection first. up here. We'll put gases down here. We'll do liquids. Then down here, we'll have force convection. Also with gases and liquids. And then down here at the bottom, we'll have convection with a phase change. So condensation and boiling. And then over here to the right, we'll have our H values measured again in watts per meter squared times Kelvin. So for gases undergoing normal convection, our H value is typically pretty small, somewhere on the order of 2 to 25, okay? In liquids, this is appreciably higher, somewhere on the order of 50 to 1,000. For forced convection of gases, we're effectively increasing our H value by an order of magnitude. So 25 to 250 is typical. And similarly in forced convection of liquids, it's an increase in an order of magnitude roughly, so 100 to 20,000. When we have convection with a phase change, so we're boiling water or condensing water, condensing steam back into water, our H value is somewhere between 2,500 to 100,000. So our fourth and final method of heat transfer is radiation, where radiation describes heat transfer through electromagnetic radiation propagating in a vacuum or air. Mathematically, this is described as uppercase E, which, let's see, what have we used this for? Young's modulus. So this is definitely not Young's modulus. Emissive, I put one too many M's and one too few S's. So this is the emissive power measured in watts per meter squared, and it will be equal to epsilon, which in this case is very much not permittivity. So this is the radiative emissivity. Somewhere between, it's a unitless quantity that lies between 0 and 1, so effectively says it either doesn't radiate or it radiates well. Then we have sigma, which is not conductivity or strain. Now it's going to be the Stefan Boltzmann, I think Boltzmann has 2 N, constant. So sigma will be equal to 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth power. And then we have TR to the fourth power. Where TR is the absolute temperature. So measured from absolute zero, obviously measured in Kelvin. So these are our four types. For the most part, we are largely going to worry about conduction, which is something that we can easily control, and then assume the other are negligible in any problem that we work. But I want to talk about the differences between the four and how we can see them. So I'm going to draw a terrible picture here of a pot of boiling water. So here I have a pot, or the cross section of a pot, and said pot is on top of the heating element of the stove, and said pot is full of water. So up here above our system, effectively we have our air temperature, and down here at our heating coil, we have the temperature of our coil. So let's describe the heat transfer mechanisms that are going on here, right? So our coil is transferring heat to our pot via conduction, right? So we have conduction from coil to pot. So that's our first heat transfer method. Once the heat that has been transferred from the coil reaches the interior wall of the pot, then we are going to have heat transfer to our liquid. So this is going to be convection from pot surface to the liquid. If our water is still, it is natural convection. If we stir the water, it is forced convection. Because if it's still, it's natural, and if it's moving, it's forced, right? So effectively, what we would see happen with still water would be the water that's in contact with the surface of the pot will heat up. And then because of the temperature gradient between that outside edge of the water will be warmer than the water in the middle, the water will move of its own volition to eliminate that temperature gradient. We're just trying to maintain a constant temperature throughout the bulk of the water. That movement of hot water towards the middle causes heat transfer to occur. And then it happens faster if we stir the water because we're helping its movement.
Is forced air convection on this.
Yep. Speaking of air convection, that's what we see at 3. We have convection from the water surface to the surrounding air. We also have convection from hot surface to the surrounding air. And lastly, we have radiation from the heater coil to the surrounding air. Now, this is a simplified thing because we're just assuming our temperature gradients are simple. We should also expect that the thermal mass of our pot will also radiate heat to the air and all that kind of stuff too, but it's just going to make the model more and more complicated. I just wanted to show that when I made spaghetti last night, I experienced 5 different forms of heat transfer. So heat transfer occurs whenever a temperature gradient exists. The ability of a medium to transfer heat between 2 points is quantified by its thermal resistance. So the greater the thermal resistance, the smaller the rate of heat transfer occurs for a given temperature difference. Right. So let's say that I have a rod. My rod has some length L, some cross-sectional area of A, and it is made of a material with a particular, make sure I'm getting the terminology here right, thermal conductivity. So the material itself has some fixed value of K. So if I put something hot on this side of the rod and something cold on this side of the rod, we can quantify the thermal resistance of our, right? So in general, Q, where this is the total heat flow due to conduction, is going to be simply our conductive heat flux times our cross-sectional area, which will be negative K times the change in temperature, because it's just negative K times the derivative of T with respect to X. So that's going to represent the change in temperature over the length of the rod. And then we multiply this guy by the area. So what we can do is we can draw an analog to electrical systems. The change in temperature is driving the heat flux. So if we treat the change in temperature as a change in potential, a voltage, and we treat our heat flux, which is moving through our rod like current, we can define a thermal resistance that is going to be the magnitude of the change in temperature divided by our heat transferred, and we get 1/K times L over A, which looks incredibly like electrical resistance, which is 1/electrical conductivity times L over A, right? So let's work a simple problem involving this concept. So let's say that I have a situation like this, okay? So this is effectively a gap in a wafer, okay? So we've etched a trench. So everywhere outside of here is our substrate. And across this trench, we have formed a suspended cantilever beam. Okay. So this thing right here is our beam. And for the purposes of this example, this beam is made of silicon nitride. That's what the material constant that we're going to use. Deposited atop our metal leads. Like so. Which have a length L. And then I'll define the other dimension of this thing in a moment. And then connecting our two metal leads is a simple serpentine resistance that's acting as a heater. So that's metal. This guy right here. And defining the other dimensions. So we have something that looks like this. So we have the width of our beam, the thickness of our beam, and then deposited on top of this guy, we have the width of our metal and the thickness of our metal. So let's say that this value is 8 microns. Our thicknesses will each be 0.2 microns. This guy is 10 microns. Our length is 100 microns. And we're going to assume here that the mass or the thermal mass of our substrate is so much larger than our beam assembly that it's effectively acting as a heat sink, such that our substrate will be at a constant temperature. Let's say our substrate temperature will be at a constant room temperature of 27 degrees Celsius, not 27 Kelvin. That'd be really, really cold. So if our beam material, silicon nitride, has a K value thermal conductivity of 5 watts per meter Kelvin, And our metal, which in this case, we're going to call it aluminum, has a thermal conductivity of 240 watts per meter Kelvin. Makes sense that an electrical conductor would have a much higher thermal conductivity than an insulator like silicon nitride would have. What is the temperature of the heater if its input power is 0.1 milliwatts and we can neglect radiation and convection losses? So I'm going to draw a thermal circuit here. Okay. So at the top, which is where I'm going to assume the hottest part of our system is, we have the temperature of our heater. And it sees multiple paths to the lowest temperature in our system, which I'll put down here, which is the temperature of the substrate, right? So it's going to have a path through the metal on the left. So I'm going to call that RM. It's also going to have a path through the beam on the left. So let's call that RB. There's a path through the beam on the right. And there's a path through the metal on the right. So the equivalent thermal resistance is going to look like 2 over whatever the thermal resistance the metal is, plus 2 over whatever the thermal resistance of the beam is, to the inverse power, because we can combine these thermal resistors just like electrical resistors do. So the resistance of our metal is simply 1 over the thermal conductivity of our metal times the length divided by the width of our metal times the thickness of our metal, which is going to look like 1 over 240 watts per meters Kelvin. So my meters and Kelvin are going to be up top. My length is 100 microns. My width is 8 microns. My thickness is 0.2 microns. So this comes out to be 2.604 times 10 to the 5 kelvins per watt. For my beam, same equation, but just using the different geometric properties and the different thermal conductivity. We're going to have 1 over K sub B times length over width times thickness, which will be meters per Kelvin divided by 5 watts. Same length, 100 microns. Now we'll have 10 microns times 0.2 microns. And this is going to come out to be 1.0 times 10 to the 7 Kelvin per watt. So it makes sense. The material with a higher a higher thermal conductivity. Make sure I'm using that right. Yeah, thermal conductivity exhibits a lower thermal resistance, right? Excuse me, substituting in the values for the thermal resistance of the metal and the thermal resistance of the beam. We wind up getting an equivalent thermal resistance of 1.269 times 10 to the 5 kelvins per watt, which is fairly close to just half of the thermal resistance of the metal, which we would expect when we have something small in parallel with something large. It's going to be slightly smaller than the smaller of the two thermal resistances. So for the most part, we could have neglected the thermal resistance of the beam here, and really it wouldn't make a whole heck of a lot of difference. And then from this, we are effectively going to write a Kirchhoff's voltage law equation where temperature is playing the role of our voltage, right? So the temperature of our heater is going to be the temperature of our substrate plus the equivalent resistance, the equivalent thermal resistance of our beam structure multiplied by our input power. And so this is going to be 27 degrees Celsius plus 1.269 times 10 to the 5. Let's call this degrees Celsius per watt. Since 1 Kelvin is 1 degree Celsius, I feel like that's a pretty fair conversion. Times our input power of 0.1 milliwatts comes out to be 39.69 degrees Celsius. And so our change in temperature was 12.69 Kelvin, or 12.69 degrees C. Again, neglecting that we can have losses due to radiation and convection.
The power plays the role of current.
Yes, absolutely right. All right, so that's a simple, straightforward kind of thing here. We're not quite ready to talk, or actually, let me rephrase that. I'm not quite ready to talk about this because I don't have any notes made on it, but it should be fairly obvious. What would we expect to happen if we had a situation like this? This is going to bring us to what we're going to talk about on Friday. So how could a structure like this be used as an actuator? So that is definitely somewhere that thermal actuation is used, but I'm talking about literally this structure. How could it behave as an actuator?
Expansion and contraction.
Exactly right, thermal expansion, okay? So this particular structure is what's called a thermal bimorph because it's made of two different materials, and those two different materials are going to have different coefficients of thermal expansion. So effectively, if we have two different materials that are, or in this case, it would work if it was just one, but we have two materials that are pressing against each other, and if we assume that the substrate isn't going to deform, when we heat that structure, the whole cantilever is either going to wind up deflecting up or deflecting down to take into account that thermal expansion. So if we want it to deflect up, we want to make sure that the material on top has a larger coefficient of thermal expansion than the one on bottom. If we wanted to deflect down, the material on bottom needs to have a larger coefficient of thermal expansion. The concept of a thermal bimorph has actually been in use outside of the MEMS realm for decades at this point, because that is what the control system of our home HVAC units use to tell whenever to turn the AC on or off. It's just a bimorph coil. So it's two materials with fused together with two different coefficients of thermal expansion, and that coil expands or contracts due to temperature changes, and it will touch a contact when it expands so much, and we actually spin the coil when we turn the temperature knob to make it slightly closer to or slightly further away from that contact. That is exactly what it is, 100%. That is.
They have something similar.
Yeah, how is that in that?
Piece of metal spray with a paper on one side, as the paper gets, wet or moist and get to expand, which causes this very thin piece of metal to expand outward, just in the top.
Okay, I was not aware of that, but yeah, so this concept of bimorphs and all that kind of stuff is all over the place. All right, so wrapping things up for today. Thermal resistance is related to the speed at which temperature changes can occur as well, right? So if we have a MEMS device, it's usually important to us how quickly we can heat or cool that device, because that tells us how quickly we can cause a displacement, right? So this is outside of the scope of the example problem, so I'm just going to put a line there. So this equation Q, where this is stored thermal energy, G measured in joules, is equal to SH, which is the specific heat. Getting back to literally stuff you guys that were here as undergrads learned in your engineering 121 class. Joules per kilogram degree Kelvin times mass times change in temperature. So stored thermal energy is just specific heat times mass times change in temperature. Well, specific heat times mass is the heat capacity. Measured in joules per Kelvin of the medium times our change in temperature. So this heat capacity in a thermal system is analogous to capacitance in an electrical system. So from this, the time constant for heating and cooling something is going to be the thermal resistance times the heat capacity, just like the time constant for an RC system is the resistance times the equivalent capacitance. So this effectively tells us how quickly we can heat or cool structure. All right, so that's all that I had prepared for today. So on Friday, we'll talk about multi-material actuation, so biomorphs and how they behave and all that kind of jazz. And we'll also talk about geometries that use a single material, so like chevron actuators, actuators that use a hot and cold arm, all that kind of good stuff for displacements in single directions. All righty, I will see you all on Friday.
So in this heat rate towards electricity now is stored thermal energy, it's charge.
So stored thermal energy, I think it would just be stored energy, right? The energy stored by a capacitor. So voltage, let's see, voltage times capacitance, so that would be charge, you're right. Well, and it works out because the symbol for charge is usually Q, so I'll be damned, yeah.
Yeah.